Earth Science Minions, video 4. We're on this page here because I ain't got no numbers. Check it. Look, Earth. See it? Earth. It's round. It's not flat. Today we're going to prove it. Or at least we're going to prove that it's rotating and it's revolving. So here we go. So, rotation movement. This is the spinning on an axis. Okay? We're going to go back and forth on these things, just so you know. So the movement for a revolution is orbit around focal points. We will get into the focal points because these orbits are not perfect circles. So that's why it's around focal points. Okay? Good. Now, periods. How long? Well, we should know that it takes 1 day or 24 hours for the Earth to rotate. Then there's some math involved. One rotation is 360 degrees. So yes, you need to write this. Divide time for one rotation is 24 hours. So you say 36 degrees divided by 24 hours. We rotate 15 degrees every hour. Okay, good. Now revolution. Math is pretty much the same, except for it's 365 and a quarter days for 1 year. So we have that leap year. Every four years, we got an extra. We lose a day, or we gain a day. One rotation is 360 degrees. So between friends, that's about 1 degree every hour. Or I'm sorry, every day. I misspoke. Okay. There's my period. Then the evidence. There's going to be a lot of videos that are going to play in here, but rotation, spinning on its axis, of course, looks like that. Revolution around focal points. We already learned all this. But here are some of the evidence. So we're going to have a few different things to write for each of these. So the rising and setting of the sun is one way to let you know that we are rotating. Also the rising and setting of the moon. The seasons is one of the evidence for a revolution, probably the main one. And the fact that we're tilted on the axis, it changes the angle of the sun. Changing of constellations. There we go. We're going to have a video on that. Movement of stars through the sky. That's the same thing, honestly. That's rotation, not revolution. Okay, so more evidence for rotation. So, Fulcrum pendulum. I want you to write that. We're going to watch a video about what it is, and then I want you to kind of sum it up in your own words. But check this out.
Step inside the physics complex on the edge of main campus, and you'll find an homage to some of the most influential physicists in history. Downstairs, an auditorium named after Stephen Hawking, who made 4 trips to Texas A&M during his life. Look down and you'll find a Penrose tiling, a pattern of simple shapes that mathematically can go on forever without replicating. The physicist it's named after is lectured here too, and he's won a Nobel Prize. Finally, look up. You can't miss it, and you'll find a Foucault pendulum hanging down from the 7th story. But this isn't a pendulum like you'd find in a grandfather clock. This one proves the Earth rotates, and there's only 6 in Texas and a few hundred in the world.
So Leon Foucault was a French physicist who lived in the 19th century. He was involved with experiments involving light and mechanics and the Earth's rotation. We all want to know about nature. We all want to understand and be able to explain why we observe the natural phenomena around us. And so this experiment is explicitly proving that the Earth rotates. And it does it in a way that is a direct measurement that we can observe right in front of us.
Dr. Dawson Noderf teaches introductory physics classes to hundreds of A&M students each year.
Some have some high school experience, but a lot of them come for the first time, and I get to open their eyes to the beauty of the natural world.
He and the other professors in his department do that by starting with simple experiments like Foucault's pendulum. I asked him to explain how it works and what it means.
So at the top of this building is the most important part. If you think about any pendulum, like say in your grandfather clock, that clock's pendulum can only go back and forth in one direction. But this pendulum has a free joint, so it can rotate and move in any way. So how does this prove that the Earth rotates? That's the main question.
So let's think about this kind of pendulum being, say, at the North Pole. Once released, it will move back and forth in one line and never change. But over time, the Earth, and us with it, rotate underneath the pendulum. So if we sat and watched, it would look like the pendulum is changing the way that it moves, but it's really not. It's us moving. From our perspective, the pendulum would seem to make a full rotation in 24 hours. Now, though, let's go down to the equator. No matter what direction we start the pendulum in, it won't appear to rotate at all. It's rotating with the Earth in the same direction. Here in Texas, we're in between the poles and the equator, so the pendulum will appear to rotate. But how long will it take for a full rotation here on campus? Remember, at the North Pole, it takes 24 hours. The math tells us our pendulum should take 47 hours, 7 minutes, and 11 seconds to make a complete rotation, and it does. The only way you can explain that is by understanding the Earth is rotating.
It's just one of the many ways that the A&M Physics Department showcases
Sorry, I was muted for that. I didn't show you the that was okay, so we should see these things moving. I don't know, button. Messing this video all up. Escape. Now I can pause. Sorry, I was trying to pause. I was going to the next videos. So we should see those constellations move at about 15 degrees an hour. Okay, changing of the constellations in the sky. So how many degrees do the stars move from diagram 1 to diagram 2? Notice this first diagram is at 9 p.m. This diagram is at 11 p.m. So 2 hours, 15 degrees each hour. So 30 degrees. Okay, notice the picture's changed. And how can you find Polaris? Polaris is the last star in the Little Dipper. Check it. It's the only one that didn't move. Okay. That's why we call it the North Star. It's directly above the, right? And then what hemisphere must you be in and why? Well, we got to be in the Northern Hemisphere because you can't see the North Star unless you're in the Northern Hemisphere. We did that before too in previous learning many units ago. Okay. What direction must you be looking? Well, north. Facts. Which direction do the stars appear to move? Oh, what causes the stars to appear to move? Earth's rotation. Again, we're on the evidence of Earth's rotation. Now we get to revolution. Parallax. Here we go. Let's check this one out. I'll remember to pause this or mute myself this time.
Have you ever traveled down a road in a car and looked at the mountains or hills in the distance? If you have, you've probably noticed that while nearby trees quickly fly past the window, the mountains move much slower, and in the far distance, the moon and the stars don't seem to move at all. As you move, objects closer to you, such as the trees, seems to shift position relative to more distant objects, like the mountains. This effect is called parallax. The size of this shift depends on the distance you travel along the road and how far away the trees are. The closer they are to the road, the bigger the shift. The same thing happens as the Earth moves around the Sun. Over the course of a year, some stars appear to move a very small amount relative to other stars. Like the trees along the side of the road, these stars are just closer than those that don't seem to move. Actually, all stars are moving through space, but much more slowly than parallax, so we don't notice. Now, if we measure how much a star moves when the Earth does one complete trip around the Sun, we can use this to work out this angle, called the parallax angle. If we observe a star when the Earth is at one spot in its orbit, and then wait 6 months for the Earth to move around the Sun to the opposite point along its orbit and observe the star again, we can measure the parallax angle. Since we already know the distance from the Earth to the Sun, we can now use this parallax angle and some trigonometry to work out exactly how far away the star is. This is really useful because it allows us to calculate the distance to nearby stars very accurately. This can then be used to check the distance measured by different methods to even more distant objects out in space.
Perfect. So that is parallax. So I hope you can sum that up in your own words. Something like objects that are farther away don't appear to move as fast as objects that are close to you when you are moving. And that is it for this video. Next one is eccentricity. See ya.